Okay, so one way to look at things is, if we look at, say, if you go into any city around the world, you look at, say, us as human beings and think of how we've sort of developed over the years, how we've sort of evolved over the years. We talked about earlier, say, whether it be sheep or dogs or any sort of animals, and think about the difference between us and an animal, so to speak. And we're going to sort of highlight certain parts of the brain and the way the brain's evolved, and look at ways that we can create experiences for ourselves and people that we work with to elicit change. Problems are lodged in the limbic areas of the brain a lot of the time, the emotional, social centre of the brain we're going to touch on. A lot of these things are phylogenic, they reach primitive sides of the brain, and they form these maladaptive psychological patterns. So in years gone by, the way the brain's evolved, we're going to sort of touch on it as we go along and have an idea. But first of all, I want to focus on the brain and how not just powerful the brain is, but I think one thing to think about where the brain is concerned is we're going to look at how do we know all this about the brain? How do we know about brain functionality? Well, technology these days has been a big help, but we learn a lot through things that have happened in the past to the brain. Now, one thing you could say is that if you damage the brain for one reason or the other, even minimally, even a small change in the brain can make a big change in personality. The smallest change in the brain can make a huge difference to behaviour and functionality. If you were driving along, or if you were walking down the street and you tripped over and sort of maybe dislocated your thumb, it wouldn't have any implications on the way you think, because your brain's not located there, so to speak. It wouldn't have any. But if you damage an area of the brain that size of your thumb or even a fingernail, have a major implication. And that's how we know, obviously, the brain has a big impact on how behaviour. I mean, you might be, hammering something away and hit your thumb, for example, ouch, and get frustrated. You might think twice about how you sort of hammer a nail, so to speak, but it's not going to have an impact on you, on the way you behave, as it would be if the brain. So let's sort of look at some background. The most famous brain in neuroscience, so to speak, is HM, as has been cited in the literature, Henry Mollison. And the reason being is that in 1953 he underwent surgery for uncontrollable epilepsy. And you get the research papers as cited in the research, and HM as is sort of referenced in the literature. But the contribution to a neuroscience is quite fascinating, because it sort of shows and helps us learn about brain functionality. So from 10 years of age, so the story goes, we sort of cite the literature, he's increasing seizures in the brain. There's a potential correlation with a minor head injury. Potentially that might have an impact, but that's not confirmed. But at 27 years of age, he would undergo neurological surgical procedure performed by William Beecher Scoville with the intention of decreasing the impact of the seizures on his quality of life. Now, this is a procedure that's never been done before, never been done since. For one reason or the other, in ethics and guidelines. And so what they did, the medical team, they removed the temporal lobe tissue, including the hippocampus bilaterally. How do they know that? Years later, through brain imaging. Years later, through brain imaging technology, researchers could identify what was removed in the brain, specifically. Okay, so they removed parts of the brain. It was the first time and the last occasion on which a bilateral removal of hippocampus was undertaken. So it's the first and last time. You could argue it was an unethical procedure, but what it did do in terms of learning about the brain is eliminated the epilepsy. That had stopped based on the research. So it's referred to as HM in all the published studies. But the only thing was, he had no capability in forming any new long-term memories for the rest of his life. He had a condition, what is known as anterograde amnesia. So he could no longer form any long-term memories beyond that point. Okay? His earlier memories, his intelligence and capacity to learn new motor skills was unaffected. So motor skill, learning a bike, to ride a bike. General intelligence, which we'll go into more detail throughout the course, wasn't affected as such. His earlier memories, prior to the surgical intervention, could still be recollected. So something that he experienced, say, as a 5-year-old, as a 10-year-old, he could still recall that. So you might be wondering, well, what's this got to do with anything? It sort of shows how we begin to understand the brain and its functionality. Now, there isn't one part of the brain, as far as I understand, from an anatomy point of view, that controls one thing, but there are aspects of the brain that have a big impact on and correlate to certain behaviour, emotions and functionality. So you can see the bilateral loss of his hippocampus had a catastrophic effect on the conversion of current experience into long-term storage. So it has an experience, and the experience does not register. But equally in saying that the earlier memories are still there, the general intelligence is still there, and the capacity to learn motor skills is still there. Okay, so in effect the surgery eliminates the epilepsy, but on the other side of things, you can no longer form any long-term memories. And that was through the bilateral removal of the hippocampus. So the temporal lobe tissue was taken out, and it was through the scanning years later that could identify that. So that begins to understand now the brain more and more. He ended up living subsequently for 55 years in care, and his memories of life before surgery were unaffected, with that part of the brain being taken out, which we'll talk about that part of the brain. So the brain constructs our reality. The brain, you're an experience of all the things you've had up until this point. Okay, your reality is your reality, mine is mine. So we've got this nature-nurture. We're born with a series of genes and DNA with nature, but also the environment has an impact on us as well, to a point, which we'll sort of touch on as we go along. So the brain, we've talked about before, even if it's damaged in a small way, our reality can change significantly. Through trauma, through the experience, through a virus, through drugs. The list isn't exhaustive. And that's just to give you an idea in the sense of how we begin to understand how the brain operates, as much as anything else, through when damage is done to the brain. How does that impact the person? How does the person behave prior to the situation and afterwards? So, okay, we talked about hippocampus there. In HM, we sort of can think about the literature on, let's look at another aspect of the brain as well. So if we look at a paper, the 97 paper, The Sniper in the Tower, Charles Whitman. Now Charles Whitman, interestingly enough, on a morning in August 1966, he was an ex-Marine studying architecture at the University of Texas. He got up one morning and he, so the story goes, I think off the top of my head, he shot his wife, his mother-in-law, or his mum, I don't recall, but what he ended up doing in the end, he got on top of the Bell's Tower at the University of Texas, and he positioned himself at the top and started shooting. And he killed 13 and wounded 30, or along them lines anyway. But anyway, cutting a long story short, the significance of that is that he was having counselling, so it says in the literature, for a period of time. And mood was becoming more and more erratic, so to speak. So he was having counselling, and you couldn't understand why. He was getting more aggressive and what was going on. And he was having all that, but he was really struggling, and quite frighteningly, he wrote that he wanted to have his brain autopsy after he died in a letter to be examined, and the pathology found a tumour close to his right amygdala that was described the size of a pecan nut. And okay, was it that correlated to the behaviour, the amygdala? We talked about that in the first 4 days. We're going to talk about again. Was it that pathologically? Well, there would have been some sort of correlation. Had it not been there, it's probably less likely he would have adopted the aggression he had. We talked about the role the amygdala has, one of the roles in the fear response. So what does that do? We get a better understanding. So, okay, now we know more about the amygdala to the point that if there's any damage there, or it can potentially alter one's behaviour significantly. The HM story where, okay, the parts of the hippocampus removed and it altered his functionality to form new memories, and now the amygdala we talked about, and I talked about my story and the amygdala in the first 4 days, where I was walking home one day from school as a 15-year-old, to reiterate, and to give you an idea of how the amygdala works. In simplest terms, one of its functions is the fear response, and as I'm walking home from school, someone races out of their home and he starts sort of waving this sort of thing that looked like an axe and starts shouting at me, and I just sort of stopped there and thought, wow, as you do, but that stopped after about 30 seconds. I carried on walking home. I told my friends and family about it, and they kind of, as you do type thing. But even though I'd caught the bus 3 or 4 days after that, on the 5th or 6th day I decided I'm going to walk again, and even though that person wasn't there, I still saw him, a figment. I started ruminating over it, thinking, should I have done this? Should I have done that? Should I have stood up to him? Should I have run? So I could sort of hear. So that's sort of the amygdala. And we've all had that. I'm sure you guys have had that too, where you've been in situations where the threat is not there, but the brain finds a way to recall the memory. And the amygdala promotes a degree of aversion to keep you safe, to keep you alive, to avoid and avert danger. Okay, to avoid potential risk, because the brain's job from that component is to keep you alive, survival of the species. So we sort of touch on parts of the brain there. And tomorrow we'll talk about other things that have happened in the history for us to learn more and more about the brain. So over hundreds of millions of years, the brain's evolved from simple organisms. Okay, so the response was moved towards positive stimuli and away from negative ones. A little bit like, say, if you see a pond and there's fish in the pond and you clap your hands, they come towards or away. You shine a light and they go away or towards. So from a simple organism, we would move towards or away. So that's the beginning, stimuli. Then we evolve, we become a bit more complex. We integrate this into what we have a spinal cord, and we start to develop more complex reflexes. So evolutionary, start to have a more complex reflex system, the spinal cord. On top of the spinal cord, we have a brainstem. And the brainstem is an outgrowth of the spinal cord, where reflexes become a bit more sophisticated. We become a little more sophisticated in the way we sort of reflex things. Example is the automation of organs. Okay, our heart and lungs. How often throughout today do you need to tell yourself how to breathe or your heart to beat? It just happens automatically. It's automation of organs. So the brainstem is responsible for that. Okay, the brainstem. That's why the brainstem is instrumental in deciding whether someone's alive or passed on, so to speak, because obviously any damage around there, significant damage, then your breathing, your heartbeat that happens automatically isn't going to happen. Okay, so that's the brainstem. Then you've got another phase of complexity. So we're building layers here. Okay. So far, so good. We're building these layers. We have what we call the hypothalamus. And this has developed basic problem behaviors, a more complex behavior. Things get a bit more complex now. The hypothalamus is about the size of an almond in human beings. It regulates important primal behaviors. And those behaviors are, we'll touch on shortly, but just to reiterate, so we're all on sync here, we develop the spinal cord, first step, then we start developing a brainstem, then we develop the hypothalamus to control basic behavior. Okay, one layer upon a layer. Okay, and the hypothalamus controls basic motivational drives. Okay, not for example to attend a seminar in the evening or today. For example, appetite first, reproduction. So the motivational drives are around survival, not come to the course this morning or seminar tomorrow night. Okay, and to give you an idea of the hypothalamus, years ago they did experiments that aren't ethical. You wouldn't do them now, and I don't want to upset any animal lovers. I wasn't involved in any of these before my time, but to give you an idea from the literature, is that they would take the hypothalamus out of cats and dogs, and they would still be functional. So they had the entire brain, except the hypothalamus, but the dogs and cats would eat, drink, and reproduce. Now you might be thinking, well, I'm not a cat or a dog, but we share a lot of our DNA with animals. I think with a dog, I stand corrected, the last bit of literature I read, I think it's 74% the same gene in that respect. Obviously different sequencing. We're 98% chimpanzee. The different sequencing, obviously, but then each individual's got different sequencing anyway. So without the hypothalamus, they could still eat, drink, and reproduce. So this starts giving us an idea of what is implicated in different aspects of the brain, which obviously are interlinked as well, which we'll touch on as we go along. The hypothalamus, it's a small part of the brain, it receives a lot of inputs, very primal inputs, basic behavior about our well-being. Hypothalamus gets input from our eyes, from light. Is it time to be awake, asleep? And I think that correlates to hunting and running away. It correlates with circadian patterns, the rise of cortisol in the morning. When the sun comes up, the cortisol goes up, cortisol being the stress hormone, which increases persistence in the brain. And it's good in moderation, but not good long term. So, okay, in the morning, we're high in cortisol, and we drop at about, say, 9. And then throughout the day, we get a spike, and we're lowest in cortisol in the evening from 9 till 12. So you can sort of correlate that. In the morning, okay, it's time to be more alert. Okay, it's time to hunt. It's time to do the things that we do when we're, the lights. Okay, when it gets dark, it's time to sleep and rest. We can't do any hunting in the evening. So it gives you an idea from the Zeitgeber, the hypothalamus, also gets input from the hippocampus and the amygdala. And we talked about the hippocampus very briefly, and we'll talk about it more as we go along, and the amygdala, because it's bilateral outside of the brain. So memory production, they're involved in memory production. So then memories aren't necessarily stored, they're not stored in the hippocampus, so to speak. It's involved in memory production, so the memories are being drawn from other parts of the brain, which we'll talk about as we go along. It's the misconception that somehow you store this memory in the hippocampus. It doesn't quite work that way. Okay, we're drawing it down. Now, the point being, we talked about how parts of the hippocampus were removed in the HM case, and we talked about the damage in the amygdala in the Charles Whitman case, and we saw dramatic changes in their behaviour, or ability at least to form new memories, and obviously the behaviour that become a lot more erratic in that respect. That's not to say everybody who gets any damage here is going to do what they did, or there's no two cases the same. Not everyone who has a brain trauma or damage is going to behave the same as everybody else. But the point being is that, okay, we're making a point about understanding the brain better. So memories input to the hypothalamus tell us what we've learnt before. So what have I learnt before? Aversion. So I won't do it again. Okay, you start forming memories. What should I avoid? So, okay, fire hot. I'm not going to put my hand on the stove now. Rejection. I'm not going to do that no more. It doesn't feel good. Being around people who you feel comfortable being around. See, because human beings, you could argue, are quite tribal in the way that we are. And that stems from, if you ostracize from the tribe all those thousands of years ago, or millions of years ago, what would the problem be, do you think? If years ago, if you sort of got ostracized from your tribe, what would be the problem, do you think? You wouldn't survive. You struggle to survive on your own. So we're quite tribal. So we're afraid of being ostracized from our tribe, not fitting in. So we try very hard to fit in because we think it's going to increase our chance of survival from the point of view of the brain evolutionary history. Even though, there's a very good chance you're going to be okay in one respect, but equally in saying that, we kind of look for places to fit in. So importantly, the hypothalamus gets input from serotonin and noradrenaline, which you've probably heard about, but we'll touch more on as we go along in the course. And it's involved in basic motivational behaviour, primal behaviour, appetite motivational behaviour, for want of a better word, the technical way of putting it, water, food, sex, basic primal behaviour. So survival of species to keep ourselves alive. Okay? It's not involved in higher motivational processes like going to a seminar or whatever. Okay? It's involved in our primal motivational. Seeking out water, food, sex, so the species, hypothalamus. And so we've covered like many millions of years in a few minutes, by the way, to give you an idea of the brain's evolutionary journey and history. And to reiterate, the brainstem correlates regulating organ functioning, heart, lungs. The basic organisms become more complex with the hypothalamus, more complex behaviour. We seek food, we seek water, reproduction. It's more complex. The next stage is the limbic system and hippocampal formation, okay, which we sort of touched on in the beginning. And to give you an idea, a really interesting piece of research, by the way, by Maguire et al. From really, really fascinating piece. If you get a chance to read it, do read it. And she studied taxi drivers. And they found in the research that the taxi driver would imagine a route, so to speak, and while undergoing functional brain imaging, the hippocampus showed increased activity. So that part of the brain we talked about earlier that had been compromised in HM because it had been taken out for the epilepsy in that procedure, the taxi drivers were asked to imagine, let's say, you guys obviously know London well, so London, okay, I've got to get from Highbury to Tottenham by taxi, and just imagining it showed activity in the hippocampus, activity. But what's really interesting as well, they discovered that taxi drivers have a larger hippocampus volume than general drivers. It's quite fascinating to think that, okay, you might think, what's so big deal about that? Well, is it the chicken or the egg? Do you choose a career based on your hippocampal volume? Because you've got this volume, you're naturally adapted to that. Or do you increase your volume hippocampi because you're sort of having to recall these journeys? Because back in the day before the sat nav, by the way, which some of the things that we've got now, you could say, okay, can you get me to where I've got to go? Can you get me to London Victoria? And they could be the other side, they could be at London Bridge, and they just, yeah. Okay, can you get me to Croydon? Can you get me to Surrey? Okay, and they could just, yeah, jump in, they can recall it. So the research suggests the correlation between the time spent as a taxi driver became a volume. So in a way, what was apparent by the researchers that actually the correlation was between years spent as a taxi driver. So that sort of environmental factor contributed to a larger hippocampal volume. Okay? So we're sort of going to touch on a couple of things. Internal navigation across space and time. Let's say you're at a social event and you're telling colleagues about a holiday and what you got up to, or the film you watched at the cinema. It's almost like you transport yourself to that experience. Have you ever been in a situation where you've told your friends about a vacation, what you experienced, what you saw, what you felt, what you heard, or a film you watched? You know, I've been in that situation where someone, what did you watch? What was it like? Guess you might have gone to watch The Greatest Showman. You might have gone to watch, say, a scary film. Every respective, and you elicit the feeling. You might have gone to watch Bohemian Rhapsody. It didn't matter what you watched, what you did, but you could sort of recall. You kind of navigate across space and time, so to speak. So, you know, what's quite interesting from the point of view of the taxi driver study is that they increased the volume of the hippocampus, and that's fascinating, which we'll talk about more as we go along. But also, we learn a lot about that part of the brain from other things too. So you've got pathological conditions, such as Alzheimer's. And if you read the research literature, there's a paper that talks about the correlation between reduction of the hippocampus in Alzheimer's. This paper by Schuf et al. 2009 talks about the volume loss in hippocampi and Alzheimer's and a reduction in cognitive ability. So the hippocampus gets reduced and the cognitive ability begins to get reduced too. Okay? So there is a correlation there, but not only in that pathological condition, also in, say, post-traumatic stress. Bond et al. 208 talks about reduced posterior hippocampi volume in post-traumatic stress disorders. And this is a similar theme in what the research suggests across other pathological conditions like depression and stuff like that. So there's a correlation there. And what it does do is it gives a really interesting outlook in terms of, okay, brain functionality. We begin to understand the brain better through it all. It's an important media that affects throughout adulthood. Now, okay, let me give you an example shortly. So now we sense the sense of vulnerability of parts of the limbic system if they're damaged. They may correlate to disorders ranging from a spectrum of maladaptive. So any damage there, whatever caused the damage, is going to have a maladaptive effect in the person. Now, you know, you could argue, for example, at birth, the baby has all 100 billion neurons. It's amazing to think how many neurons we have, but the environment influences as well. So 100 billion neurons are pretty much in place when you're born. But equally, the environment then, we talk about epigenetics, we'll cover that on the program a little bit in some detail, is influenced by the environment. So something as simple, for example, the baby cries itself to sleep or himself to sleep to avoid the pain. So you leave the baby falls asleep. In the first year of the life of the baby, it's when the brain development is accelerated. So the baby is, you know, said, you know what, out of sight, out of mind, the baby falls asleep on its own. but then the baby starts developing a feeling of not being wanted or needed. And that could have a correlation with behaviour. Because as the baby, the baby bonds, oxytocin, the chemical bonding between the mother and baby, and in a functional biochemical mum, she builds oxytocin, and the baby needs love, needs nurturing, needs all these things the baby needs. But then the baby's put to one side to leave the baby to cry, and people say, well, the baby cried to sleep, but the baby doesn't fall asleep gently. It falls asleep to avoid the pain. And when you think about that first year and how significant it is when the acceleration of early brain development, and what is the perfect environment? But the point being is that, to give you an idea of brain how it develops, the outside influence. So these can influence the baby in that respect. So you might think, well, what the hell is he on about there? Well, what I'm on about is the fact that in epigenetic study, and I'll cite the literature, but there's been literature, some of the literature suggests that the rats, for example, academia had a link to the literature that I read about the experiments around the rats, and the rats that are born in an environment that, well, the experiment was based on the rats with, the group of rats was segregated between high-licking mothers and low-licking mothers. And in a world of rats, high-licking correlates with love. And these babies were fostered. They weren't put with their maternal parents by the maternal mothers. Some of the babies were put together with the rats that were high-licking in that first week of being born. And some rats were put in the environment with the low-licking mums. And there was a correlation there even years later. The science has suggested that even years later, the rats that were licked less were more aggressive and anxious and more likely to go after a researcher than the ones that were in an environment where they were licked. So we know now that the first year is damn crucial. We know that on the brain's development. So that kind of knocks out the nature-nurture. The debate that's long gone now. We've got to think, well, both things are factors. Epigenetic. So epigenetic these days tell us that, you know what, and neurogenesis is that throughout life we do produce new cells. We can be influenced by the environment. There are things that we can do experientially that have an impact on our brain. Yoga, meditation, food, diet, nutrition, all have an impact on our behaviour to a point. And that's what we're getting at, is that the limbic and hippocampal emotions, connection, memory, habits, crucial for development, the evolution of the nervous system. So each time a new part evolved on top of the earlier parts, this is why we have deep parts of the brain, parts that are under the surface, the cortex, they're more ancient. Okay? So limbic system and hippocampal formation are quite deep in our brain. They are deep in our brain. Okay? The limbic system is raw emotion, anger, fear, happiness. Raw emotions separate the thought, the process of frontal lobes, which we're going to get to shortly. It's an ancient development, the limbic system. Emotions act as drivers, fuels for actions, behaviors. We rationalize through our prefrontal. So we're different to the animals around us because we've got a part of the brain that makes us capable to do the things that we do, to survive. So we develop an emotional system on top of the more basic survival system, and the limbic system uses experience, memory, and motivation able to produce a more appropriate response. How to respond, aversion, okay, to certain situations. Now, the aversion all those years ago was different than aversion now. We don't have dinosaurs roaming the earth and saber-toothed tigers, but we live in quite a stressful world. You've got to pay the bills, you've got to do this, you've got to do that, and it produces responses in the brain, the same as it would do back then. So, very briefly on memory, you might not have rode a bike for years, but you still got the motor skill years later. Okay, who'd be confident to ride a bike now if you had to? Yeah, of course you could. So, we look at memory, recollection of old stories with friends. So you go back to a place you used to live, and it invokes a feeling. Ever have that before? Or you go to yeah, you can connect to emotion. So memory of an emotion, how you felt at the time of the experience, which is different to emotional memory. The emotional memory is the memory of an emotion, for example, in PTSD, when someone's re-experienced the feeling over and over again. It becomes pathological. So I mentioned the story about me, the guy comes running up this sort of axe type thing, and I don't have any issues with it now, but if that becomes a recurring theme, that's the pathological condition of, you could argue, of PTSD, post-traumatic stress. So it becomes the recollection of the experience all the time. Okay, it's there. It's set off by an air conditioner that reminds someone of like a plane, going overhead in combat. It's set off by seeing someone that looks or reminds them of someone that were aggressive towards them years gone by. It's set off by smelling something or tasting something, or sparked by a sensory perception of a situation. So, the limbic system, the hypothesis is the limbic system evolved to give us a memory of the past, to evaluate new situations, to modify behaviour. So you've got to choose, is it an appropriate response, what I'm doing? So we talked earlier about some of the responses that you mentioned. You try to talk yourself out of it. But you're trying to fight against a system that's evolved for millions of years. How on earth is one part of the brain going to talk another part of the brain out of not being afraid that the brain's made its mind up at a deeper level? Tell yourself not to eat the ice cream. You're on a diet and you see the ice cream and you say, you know what, I shouldn't eat it. What's going to win? Okay? Tell yourself not to do a behavior that you do that's fueled by an emotion. Tell yourself not to like that person, not to love that person, because that person's not good for me. It's damn hard, isn't it? Okay, so logically we know one thing, but logically, if we could do things logically, then we'd solve all the world's problems. But the primal systems have a big influence on our behaviour. Keep things experiential. So, okay, I know the guy's not there when I'm walking past in the street. I know he's long gone, but I can still see him in my mind's eye. I can still hear him. I can still sense the experience, even though he's not there anymore. Because my brain's telling me how to modify my behavior, how to adapt it. So you know, by asking that person a question, where'd you buy those shoes? Where'd you do this? Why'd you do this? What's the worst that's going to happen? So, what's the best? What really is realistically going to happen? They're going to tell you where, or they might not say, well, I don't know. But the reality is, it's not the danger we faced millions of years ago. It's not like confronting a saber-toothed tiger. And you know that. You don't need me to tell you that. And you know that. But logically is one thing and limbically is different. So you know a comment when you go into the office. It's not going to, big deal. But you feel afraid. You're afraid of being ostracized from the tribe. You're afraid of not being part of the tribe. Because then you're vulnerable then. You're scared of your vulnerability. And you're scared that, okay, if these people don't like me, they're going to ostracize me. And that's not a problem anyway. Because you go to work. And then you go home, you socialise with who you want. There's no big difference really in one respect, but you're saying at the brain, I'm afraid. And it forms a behavioural pattern. And what you do then is go to safety behaviours. Does that ring a bell? Safety behaviours. You do things that you probably wouldn't normally do to keep yourself safe. You lash out. You don't go to work. You avoidance. Exactly. We do things we probably wouldn't normally do. We don't think logically. We go into fight, flight, freeze mode. You might fight. You might freeze. You might run out the door. But one thing's for sure, the adrenaline's going and pumping. And you're making yourself damn ill, for goodness sake. Ill over nothing. Well, I shouldn't say nothing, but the reality is that big deal. Big deal. Why am I making myself ill for over people that I'll probably never see again anyway? Why am I getting myself all stressed out of something that's happened years ago? But it's not as easy as that, is it? And the limbic system is a collection of structure, not one structure, by the way. I want to clarify that. It consists of regions, hypothalamus, amygdala, hippocampus. There is some debate in the research as well, depending on which country you're in, where you studied, America, the UK. Some people say parts of the basal ganglia. That's another story for another day. But it plays a big role in learning and memory, the hippocampus, and together with the para-hippocampal region, the cortex areas that surround the hippocampus, the areas of the cerebral cortex, including the prefrontal cortex, and provide the system that supports declarative or cognitive memory. So we talked about declarative memory, very briefly before we break for lunch. Can you recall the name of a place, a name of a person, where you're going tonight, your work phone number? Can you guys recall that? Pretty easy to recall that, isn't it, to a certain extent, if everything's working the way it should work. Declarative memory, and non-declarative memories, or behavioural memories, without consciously thinking. So you've got to unconsciously go about doing what you do normally, and you do things that you do, you don't even realise you're doing it. That's non-declarative memory, in a nutshell, before we sort of break away. So, on a final one, before we have lunch, on top of the limbic system, we built a cognitive model. We've done a full circle. As human beings, we use verbal communication. And verbal communication is fine. It's fantastic. Verbal communication can get us far. I can ask you, okay, can you make me a cup of coffee? I can say that easy enough. And the answer might be yes or no. I can tell you I might have a bit of a problem. I can tell you I might need to lift somewhere. You can tell me that you might need to use the bathroom. You can tell me you might have a problem, and it'll get us so far. But how much of the way we process what we've covered so far is based on that part of the brain, which we're going to touch on in more detail tomorrow. Because in years gone by, I wouldn't have the capacity to say, can you make me a coffee? I would grunt. I would moan. And that might happen in some of your households. Yeah, precisely. And the point being is that we use those methods to get through to people and express themselves. So there are ways and means to be experiential, to get into those deep structures. We know yoga through research can do that. Why I'm a big advocate of yoga. You say, what you're going about yoga, and I do some yoga every morning, pretty much every morning. Not a great deal, but what I can do, as much as one can do, just to sort of get into that part of the brain, just for a few minutes, just a few things, to sort of get into that part of the brain, to get going again, as you do, to start the day on a positive note. Wonderful to do, as intrusive or non-intrusive as one can do, but rationality. If human beings can think their way through a problem, then they wouldn't need any therapy or coaching. They could do it on their own. Now, here's the book, go away, all the best, so to speak. And if they could have solved their problem, they wouldn't be seeing you as a therapist or a coach. They'll do it on their own. We mentioned earlier, there's sort of parts of the brain that are in play. So there is no manual. There is no step-by-step procedure or protocol that people like to adhere to that's going to fit everybody. It's about you being creative, using your creative brain. Through its connections with the prefrontal cortex, the limbic system, so as to integrate the cognitive, emotional, automatic aspects of our lives in response to stimuli from the external and internal world. So let's get to know ourselves better internally. Let's become more self-aware externally. And let's use that as the building block to helping people go, if it's your remit, from maladaptive to adaptive, from a coaching point of view, to achieve their goals. The limbic system participates in states that may be adaptive, in identifying response to threats. So we don't want to take the amygdala out, because then you have no damn fear. You run across and God knows what you do. So we need it. Not that you'd be allowed to do it anyway. But let's get a better idea of what our threats are. Let's be more clearer. Let's be more self-aware. And not work in survival mode. Because the damn world these days, everyone's damn working. A lot of people are working in survival mode. They've been stifled by the damn media into maladaptivity. The media, every day you read the papers, anywhere you go in the world, by the way. Everywhere you go in the world, it's all damning, man. It's all damning in the media. And that sort of creates that limbic response. It keeps people in that frightful survival mode response. And it's not a good place to be. And it starts at schools. Schools, you know what, you don't do your homework, you won't go to this and you won't do that. And, it's great if you want to control people to a point. But equally in saying that you're not fostering or creating a healthy environment. It's not good to live that way. And the world we live in is not going to change in a hurry in that respect. So you know yourself and you adapt to this world that we live in, and start by not even borrowing the newspapers. I don't bother the news, the newspapers, and sort of be more self-aware about who I spend time with too, by the way, because that has a big, big impact. That's another story for another day, because obviously, the world, and also integrating a system, an ongoing system, yoga, meditation, eating well, resting well, very important things to look after ourselves. Just before we sort of break away, the olfactory system is the only sensory system that goes straight to the limbic system without relay to the thalamus. So the smell is the only thing that goes straight bang to the limbic system without any relay from the thalamus. That's another story for another day. But anyway, on that note, we're going to break for lunch, and we'll open for questions after lunch, and then we'll crack on with the rest of the stuff. So.